Two balls in a bowl and the moon, how does that hang together? Everyone learns that angular frequency of simple harmonic motion depends on the square root of the force constant of the restoring force divided by the inertial mass m of the oscillator. Now, here I've got a ball, which may be circular in curvature, and I've got an oscillator, a little ball bearing. It oscillates nicely with a certain frequency. Here I've got another ball bearing, clearly much more massive. Again, it oscillates nicely with a certain frequency. But hang on, don't they both have the same frequency? They have. Isn't that a contradiction to what we just said? Frequency depends on mass. The big one is clearly much more massive than the small one. How can we understand this? Let's draw the situation. We have the origin, which defines the curvature of the ball, and in that ball we have the ball bearing at a distance of maybe L from the origin and displaced by an angle of theta. The restoring force Fr acts tangentially in regard to the curvature This is the ball radius and its curvature, and the restoring force acts tangentially, and that tangential force is provided by the gravitational mass m of the ball bearing times gravity, m times g. So we have a component of gravity restoring the displacement, or trying to restore the displacement of the ball bearing to 0. And that component we can work out by considering the geometry. We have theta here, we have theta here again, the displacement angle, we also have it here. So therefore the restoring force F of R, Fr, is equal to minus, because it always acts in opposition to the motion. It is minus times the sine of theta times m times g. Yeah, Fr divided by mg is equal to the sine of theta. Therefore, this equation holds. This is our restoring force. Now, for small displacement angles, if theta is small, if it goes to 0, if it's of the order or smaller than something like 10 degrees, we can make the following approximation. We can say the sine of theta is approximately equal to theta. However, now not measured in degrees, but is measured in radians. And with that approximation, we can simplify our equation. We can get rid of the sine function in there and write the restoring force is equal to, Fi is equal to minus mg, the gravitational force, times theta in radians. That is the crucial equation. And the force constant in here is not quite clear yet, because we don't have the x. Yeah, remember, we need to work out how this equation relates to minus force constant times x. So we have to express the theta in terms of x. But that can be achieved by considering the length L, the distance from the origin of the curvature. And we find that theta is given by x divided by L. For small angles we have, this is the right angle, and this becomes L, so theta divided by L is equal to the sine theta, and because we now again use this approximation that theta is small, so we can simply say theta is equal to x divided by L. So we therefore have in this equation minus mg times x divided by L, by the length L. So now we know the force constant. Now we know this is our x, so the force constant, K is equal to gravitational mass m times gravity divided by L. And that we can now substitute into this equation, because we're going now from here to there, and we write omega, the angular frequency, is equal, for any simple harmonic oscillator, the square root of k, so that's our force constant, m, times g divided by this length L. And we have to divide by the inertial mass, and you now notice that there is a difference between the gravitational mass at the top and the inertial mass at the bottom. One acts in its gravitational capacity, the one at the top, and the other one acts in its inertial capacity. However, because of the equivalence of mass introduced by Newton, we can now cancel one with the other, and we obtain that the angular frequency of a ball in a ball is equal to the square root of g divided by L. That is a very important result. Now, this doesn't just apply to balls in a ball, but also to a pendulum, because the situation for the pendulum is exactly the same. You have a length of string, and you have a point mass or a ball bearing at this string, and it oscillates back and forth under gravity, and therefore for the pendulum we've got the same equation. The angular frequency is equal to the square root of g, of gravity, the square root of gravity, g, divided by the string length. Now this is a very useful concept, because it allows us to learn about gravity, since the length of a string is easily determined, and we can determine the gravity on Earth. But more importantly, we can prove that the moon landing was really true. And that can be done if you look at some footage from that era, and you see that there is an accidental pendulum. There it is. There it oscillates nicely, because during equipment offloading from the scientific equipment bay, the cord become unstuck and oscillated nicely, and we now have live footage of that oscillation, and you can check out for yourself if that period, if that angular frequency is consistent with that pendulum being on the moon and not somewhere in the Nevada desert.